Okay, so here we go on Unit 2, Forces and Newton's Laws, our first lesson on some basics on forces, and we're going to cover Newton's first and second law. And our goal here is to kind of get a qualitative understanding of these two laws. Now, by themselves, Newton's laws are really just three short little statements, okay? And they seem pretty simple, but once we start unpacking them, we're going to be able to look at a motion in a very different way than we've looked so far. Let's start by asking two questions. First, if an object is moving, what are some ways to make it stop moving or make it change direction? And if an object is not moving, what are some ways to make it start moving? As we look at things and we think about things, we could name out a bunch of different words that we could do to make things move. We can pull it, we can push it, we can hit it, we can slide it, all these things. But what all those boil down to is a simple push or pull. And that's all that a force really is. It's a simple push or pull. Like anything that you can think of that would cause an object to move, stop moving, or change direction can really be boiled down to being a push or a pull. And that is what we call a force. So there's some basic definitions to have an understanding of before we can get much further into forces, right? Inertia. Inertia is a property of matter that resists its changes in motion. Okay, so an object that has a really big inertia, real high inertia, is more difficult to get moving or to stop moving than an object that has low inertia. Then we can talk about mass. Mass is really nothing more than a measurement of inertia. Okay, so now we measure mass in physics. Our standard measurement, our standard mass unit is the kilogram. Okay. And then, as I've said, a force is nothing more than a push or a pull. Okay. Now we can have two real basic types of forces. We can have what's called a contact force, or we can have a field force. A contact force is a force where a physical contact exists between the thing that is providing the force and the thing that is experiencing the force. Now, when I say the thing that is providing the force, that is something that's what we call the agent of the force, and then the thing that experiences the force is the object. So, and then we've got field forces. In field forces, there's no contact. Okay, so a field force, an example of a field force would be like a magnetic force or a gravitational force. Contact force would be anything that you push or pull on something and you make physical contact. So three really important truths about forces that we need to have an understanding of. First, forces act on objects. Okay. Second, forces require an agent, something that exerts the force onto the object. And third, that force is a vector. Okay, a vector again is something that has a magnitude, has a size, and a direction. Okay, so it's very important that we understand force is a vector. We're going to be able to add it vectorly, like we've done in Unit 1. So if you look at this picture here from our textbook, you can see, for this first one, this person is pulling on a rope, and the rope is attached to the box. The rope here is the agent on there. You might think that the person would be the agent, but the person is exerting the force on the rope. The rope is then exerting the force on the box. Therefore, the rope is the agent of the force on the box. As far as the box is concerned, it's the rope that's pulling on it, not the person. The person pulls on a rope. Here in this one with the spring is the agent on this box here, sliding it to the right. And here we got a field force, gravity, pulling the box down. So gravity is the earth is the agent because it's the mass of the earth that exerts that gravitational force. And in each of these three examples, we've shown each of those forces as a vector arrow, which we're going to look at how we do that next. So when we want to go to draw a force vector, we always begin by taking whatever our object is. Say we've got a box here, okay, and we've got a person who is pushing on that box, okay, and they're pushing it to the left, okay. So we want to draw the force on acting on the box. We would show the box as a dot, and the force acting on the box as an arrow to the left. We give it a label, say force of this push, okay? And there we've drawn the vector arrow for that force. Now, there's multiple forces acting on this box. There's also a gravitational force acting downward, which we could call Fg, and there's also this a force on the floor pushing the box up, which we're going to call, and we'll talk about that later, we're going to call it the normal force. And it looks like that. So a full kind of diagram. There'd also, for sliding across the floor, there may be also a little bit of friction going back the other way here. So we can call this force of friction here. Okay, that opposes the motion of that box. Okay, so this would be the full diagram of all the forces acting on that box. Now notice that when we draw this, we're drawing it as though with the tail of each force on that box, not and the arrows all point away from that box. We never draw a force diagram where we're putting the arrow on the thing, even though the person is pushing the box, they're pushing on the box. We're going to show their push as though it's being exerted on that box and being pushed away from the box. Okay. Now, as shown on that previous page, we can have multiple forces acting on an object, and when we do have multiple forces acting on an object, say we've got this box here. This is a top-down view, so we're looking down from the top, and there's two ropes attached to it, one pulling straight downward and one pulling off at this angle here. Okay, so we've got multiple forces acting on this box. If they're pulling, so what we end up with is what's called a net force. Okay, we can combine forces and come up with what's called the net force. And so it's that net force then that we're going to see plays a very important role in the acceleration of the box, of whatever object it is. Okay. So here in this example, we've got two forces acting on it. Those two forces then combine to create this net force here. Okay? And that net force then is the vector sum of all the forces acting on that box. We can write net force, and so we don't want to, we don't always want to write out the words net force. We can go F sub net to show that we're going to talk about the net force, or we can use the Greek letter sigma, which means sum of, to say net force. Okay, so now let's talk specifically about Newton's first and second law. Newton's first law states that an object at rest remains at rest, an object in motion remains in motion unless it's acted upon by an outside force. So like this picture here, we can see this motorcyclist had been moving at some point. A force was exerted upon him, but because of his inertia, okay, he is moving. He's no longer attached to the motorcycle. When he was attached to the motorcycle, he and the motorcycle were traveling at the same rate. And so they could be considered to be moving as one object. So when his motorcycle met these tires right there, he continued in his motion, and it's a nice projectile flying over the tires. So an object at rest will remain at rest, and an object in motion will remain in motion unless it is acted upon by an outside force. Now, I'm going to try something here with the video not done before. As you see here, I've got a browser to another video in here. Now, I just want you to watch this video showing Newton's first law, if I can make it work. It's going to reload. All right, so our shopping carts are sitting nicely in our truck, and our happy Target worker is, he's checking things out. He must be new. It's his first day on a job, or it's too early in the morning. Truck drives away. Shopping cart falls out. Workers look amazed that they are scattered all over the place. But it's Newton's first law, right? The shopping carts were at rest. They want to stay at rest. They weren't blocked in. There was no force to keep them attached within the truck. Therefore, they remained at rest, and the truck moved out from under them. Okay, so Newton's second law tells us that the acceleration then of an object is directly proportional to the net force acting on it, and it's inversely proportional to its mass. Okay, so in class we're going to do several activities to look at this relationship, but essentially the relationship between acceleration and net force is a directly proportional relationship, and the relationship between acceleration and mass is an indirect relationship. So, as explained with this picture, here we've got this feller. He's going to hit this golf ball with a golf club. Okay, if he exerts that same force on a truck, he's going to get a much smaller acceleration of that truck. Okay, so the idea is that acceleration is directly proportional to the net force on an object, and acceleration is indirectly proportional to the mass of an object, which we experience every time you go to push on a really massive thing. Say you're going to try to push a Prius. Okay, one person or maybe two people could probably push a Prius, but those same two people pushing with the same force are not going to push a large truck. Okay, they're not going to get it to accelerate. So that's showing us how our net force, our acceleration is directly proportional to the force, and it's indirectly proportional to the mass. So this can be combined into a single mathematical statement we call Newton's second law right here, where our net force is equal to our mass times acceleration, which shows us how the units of force then would be, because it's mass times acceleration, the mass would be kilogram, acceleration meters per second squared. So 1 kilogram meter per second squared is something that we call a Newton. Okay, so our unit of force will be the Newton. Okay, which brings us to this example here. So we've got Roberto and Laura. They're studying across the table from each other. Laura slides a 2.2 kilogram book toward Roberto. If the net force acting on that book is 1.6 newtons to the right, what is the book's acceleration? So we've got this book, and here it is sitting on the table. It's being slid across the table, and there's multiple forces acting on this, but we're told in the problem that the net force is right here, and our net force is this 1.6 newtons to the right. We want to know the book's acceleration. And the mass of the book is this 2.2 kilograms. Okay, so Newton's second law tells us the net force equals mass times acceleration. So here's our 1.6, 2.2. Our acceleration is this 0.73 meters per second squared, right there. Okay. So, as we do more complicated problems with this, drawing pictures, and we're gonna learn in the next unit about a specific type of picture we're gonna draw called a free body diagram, which will help us to identify all the forces acting on an object. And really, this kind of thing right here is a very, very good habit to get into as we go into solving more complicated force problems. Let's look at another one real quick. If we've got two forces, we've got 6 newtons and 3 newtons that act on this object here. okay, in opposite directions. So now we're not told what the net force is, right? But we can figure out what that net force is because these are two objects. These are two forces, okay, acting on this one object. So we've got the 6 Newton force acting over here, 6 newtons. We've got another force 2 acting here over here. It's 3 newtons. Okay. Now notice when I drew these, right? I drew the arrows proportional to the size of the force. I drew the longer arrow as the 6 Newton force. Okay. So we can see from this then that our net force is going to be 3 newtons. They're acting in opposite directions. Okay, so our net force is going to be 3 newtons acting toward the left, which is technically our negative direction. Okay, so we would throw in a negative. When you look at, we throw in the negative to indicate that net force is acting in the negative direction. When we look at our possible answers here, none of them are in, none of them show negative, just because they've obviously I identified left as the positive direction for this particular problem, but generally speaking, we would call it a negative direction. So Newton's second law tells us net force equals mass times acceleration. Our net force here is our 3 newtons. The mass of our, what is that? It looks like a dumpster. Mass of our dumpster is 100 kilograms. We want to know the acceleration. Obviously, our acceleration is going to be 0.03, so our answer will be A. Okay, so in your reading packet, there are 2 study questions right after example 1. Should be on page 5 of your reading packet. Pause the video for a moment and go through and answer those study questions number A and B. Okay, and in answering those questions, you should have come up with 2.19 or 2.2 meters per second squared for the first one, and in the second one, it should be 13.6 newtons, and you'd go about solving that second one. First, you have to use some kinematics, use the second kinematics equation to get the acceleration, then apply Newton's second law to get the 13.6. So there's a whole lot of forces that we're going to be dealing with over and over throughout the rest of the class. What I want you to do is, using your textbook, read section 4.3 and identify the following for each of the type of force in that section of your textbook. You're going to identify the force, you're going to identify the symbol for the force, identify the agent, the direction the force acts, and provide any other important information on that force, and then draw a diagram of that force. Include that stuff in your spiral notebooks, in your notebooks. Okay, so that ends lesson A.